Press enter. So there you go. 0.0322 if we go to 4 spots. Okay. And if we had done the algebra or the arithmetic on the previous page the long way, using the formula by hand, we get the same answer. Okay. So the calculator gets us to what we want, but we've made some assumptions before we use this function. First, there have to be exactly 2 outcomes that we are interested in. A success and a failure, which here was, did we roll a 5 or not? So we had 2 outcomes. And we have to have independent trials. Is it true that the result of one dice roll doesn't affect any others? Yeah. So since we have independent trials and we have exactly 2 outcomes, we can use this binomial function to find the probabilities for us. If those assumptions aren't met, then we can't use it. So let's do an example of the binomial. Okay, so a hospital wants to evaluate the success of their cardiology program by looking at the number of successful heart surgeries. And what they find is that the probability that a patient recovers, so that sounds like a success, is 90%. We can assume that surgeries are independent. So what this means is whatever happens in one surgery doesn't affect what happens in another surgery. So I think that's a realistic assumption. There's probably more than one doctor, so if one goes badly or one goes well, it doesn't affect what happens next. In the next week, there are 7 surgeries scheduled. So we want to know something about those next 7 surgeries. So the first question is, how many of the next 7 patients can be expected to recover? So what we know here is that we have 2 outcomes. The patient recovers or doesn't recover. And we have independent trials. So these 2 pieces tell us that we're dealing with a binomial distribution. Okay, the last thing we need to establish is what's our random variable. So what are we measuring? So big X, this is the number of recoveries in 7 surgeries. So what we know is we now know the distribution of X. Because we have these 2 characteristics, we know that big X, squiggly line that stands for, is distributed as a binomial distribution. And we know that N, the number of trials, is 7. And P, the probability of a success, so what we want to see is that someone recovers, we're told was 0.9. So to answer part A, how many of the next 7 patients can be expected to recover? So when we see the words expected, that means what's the average? So here, because we use this binomial distribution, we can take the number of trials times the probability of success, 7 times 0.9, which is 6.3. So we expect 90% of our patients to recover. 90% of the next 7 is 6.3. So nearly all of them should recover. That's what we expect. Now we can compute the standard deviation. So what we have is we have an equation for variance. And what that said was you take n times p times 1 minus p. So these two formulas are coming from the bottom of page 8. So we already know what n times p is. That was 6.3 from before, times 1 minus 0.9. So if we do that math, let me find my notes. Oh, it's pretty easy. It's actually 0.63. Now that's the variance. We were asked for standard deviation, so we have to take the square root. So standard deviation is the square root of variance. So we need the square root of 0.63, which works out to be 0.7937. Okay. So the way that we can interpret this is just like before. It's telling us that if we randomly pick a surgery, randomly pick a set of 7 surgeries, the number of successes we'll see is 0.8 away from 6.3. So on average, we can expect to see between 5 to 7 recoveries, is roughly what this is saying. 6.3 minus 0.8, it's 5 and some change. 6.3 plus 0.8 is a little more than 7, but we only have 7 surgeries. So on average, the number of recoveries we see should be within 0.8 of 6.3. That's what the standard deviation is telling us. Part C, what's the probability that exactly 5 of the next 7 will recover? So this is saying, what's the probability that X, the number of recoveries in the next surgery, equals 5. Since we know that big X follows the binomial distribution, we can use binomial PDF. So N was 7, P was 0.9, and we want 5 successes. So you press second vars, you can use the arrows, or you can just press 0, since we know that takes us to binomial PDF. So we put 7, comma, 0.9, comma, 5, so we get 0.1240. We'll always do it 3 to 4 decimal places. 4 is best, 3 is okay. So the way that you would interpret this, there's a 12.4% chance that exactly 5 of the next 7 surgeries or I guess patients, sorry. 5 of the next 7 patients will recover. And maybe that seems wrong, because there's a 90% success rate. And we're saying that there's a 12% chance that 5 will recover. So the key here is that we're saying we want to see 5 people recover, 2 people not recover. What's the chance that particular outcome occurs? Well, it's not going to be very likely. If we have a 90% success rate, we're expecting to have more than 5 recoveries. So this having exactly 5 shouldn't be too likely. So the answer actually makes sense. It's that we're looking for this specific outcome, exactly 5, which is unlikely given that we have a 90% success rate. Okay, so we will end is what's the probability that at least 5 of the next 7 will recover. So we want to know what's the probability that the number of recoveries is greater than or equal to 5. That's what at least 5 means. 5 or more. So really what we want to know is, we could see 5 recoveries, or, so we'll add 6 recoveries, or we could have all 7 recover. So we've already taken care of 5. We did that in the previous one. So to find the probability that x is 6 and x is 7, we'll just use binomial PDF again. So when x is 6, binomial PDF, the number of trials is still 7, the probability of success is still 0.9, and we want 6 recoveries. So on the calculator, that works out to be 0.3720, and you should verify that you get these values. We do the same for 7. The binomial PDF helps us find the equals. X equals something. It doesn't work for greater than or equals. So that's why we had to split it into 3 different possibilities. So when x is 7, we use the function again. N is still 7 surgeries. The probability that any one of them is successful is still 0.9. All that changes is the number of successes we want. We want 7 recoveries. That probability that we see all 7 recover, exactly 7 recover, is 0.4783, we'll call it. So now we have to put this all together. We still want the probability that x is greater than or equal to 5, that at least 5 will recover. So we take the answer from above, the previous part, where x was 5, plus when x is 6, plus when x is 7. So you add those up, and you get 0.9743. So in other words, the probability that at least 5 of the next 7 patients will recover is 97.43%. Okay? And maybe this is the answer you were expecting in the previous problem. But this is normally how we would think. When someone says 5 recoveries, we think, oh yeah, 5 or more. But that's not what was being asked in the previous section. The previous problem said exactly 5. That's why the probability was so low at 12%. This one is saying 5 or more recover out of the next 7. Well, that's where we expect to see the number of recoveries. Most should recover. So it makes sense that we're almost guaranteed 97% of the time at least 5 will recover, 5 or more. We'll end here. On Thursday, we'll recap Chapter 6. Be prepared with any questions you have. This video lecture moves pretty quick because I don't have questions. So we'll start off with questions, whatever you want to know. We'll briefly go through pages 1 through 10, and then we'll continue on. So, see you Thursday.